In this clip we're going to go over some of the basics of groundwater and aquifers. Now, groundwater is found within the empty spaces called pores in otherwise solid geologic material. Materials that act as aquifers. An aquifer is essentially a geologic material, sediment or rock, that has both high porosity, lots of empty space to hold water, and lots of permeability. Permeability refers to the ability to allow water to flow. And that's a function of how connected the pores are. So again, groundwater is found in geologic materials that have certain properties of high porosity and high permeability. We call those materials aquifers. They hold a lot of water, and they allow the water to flow at a fast rate. In other words, the material has both a high porosity and a high permeability. In this example, sand and limestone are both acting as aquifers. The sand has a high porosity and a high permeability. In other words, porosity and permeability are both high in sand. Limestone, likewise, because limestone can be dissolved by acidic water, will have lots of void spaces, empty space. It will also have both good porosity and good permeability. The opposite of an aquifer is an aquitard. An aquitard is a layer that restricts movement. It restricts water movement because it has low permeability. It may still have good porosity, but if the pores are not connected, that material will not allow water to flow readily. In other words, that material will have a low permeability. In this example, clay, fine-grained sediment, lots of pores, but the pores are too small to be connected. This material has low permeability. So it acts as an aquitard. Shale is a sedimentary rock made from clay. It likewise has properties of low permeability and functions as an aquitard, a layer that inhibits the flow of water. The presence of this clay and shale layer acting as aquitards makes the limestone a confined aquifer. In other words, the movement of water, vertical movement of water, is restricted, inhibited by the presence of aquitards above and below that limestone layer. As a result, movement of water into or out of the limestone aquifer is restricted by the presence of the clay and shale layers that are acting as aquitards, making the limestone a confined aquifer. The sand is an unconfined aquifer. There is no impermeable layer to restrict the movement of water into that sand layer. In other words, an aquifer made of a material like sand is unconfined if it doesn't have an aquitard and low permeability layer above it. The water table represents the upper limit of saturation within the unconfined aquifer. In other words, the vertical extent of saturation in that sand can freely rise or fall, expand or contract with changes in recharge or discharge. When recharge is high, the water table rises towards the surface. When recharge is low, the water table sinks to greater depths. The slope of the water table, the hydraulic gradient, can be approximated by the level of water in wells within the unconfined, only within the unconfined aquifer. Well A, well C are within the unconfined aquifer. There's a high water table elevation here. Lower water table at well C. And groundwater, just like surface water, flows from high to low elevation. So water in the upper or unconfined aquifer is flowing from left to right in this example. The wells that extend down into the deeper confined aquifer show the pressure that water is under because of its confinement by aquitards. That pressure surface is called the potentiometric surface. You can think of the potentiometric surface as showing the level or elevation to which water would rise in the unconfined aquifer if it wasn't prevented from doing so by the presence of the aquitard. The aquitard restricts vertical water movement, generating pressure in the lower confined aquifer. The wells that reach into the lower or confined aquifer show how much pressure that water is under based on the elevation to which water rises in those wells. In other words, the level of water in these two wells shows the slope of the potentiometric pressure surface. And again, water flowing from high to low pressure, the water in the confined aquifer is flowing in the opposite direction of the water in the upper unconfined aquifer. In the deeper confined aquifer, water is flowing from right to left in this example because the level of water, pressure that the water is under at D, is higher, and the pressure that water is under at B is lower. And again, water is flowing from high to low pressure. We can use the measured elevation to which water rises in wells in each of these aquifers to calculate the hydraulic gradient within that aquifer. We can then use hydraulic gradient in Darcy's law to calculate groundwater discharge or groundwater velocity. Hydraulic gradient is similar to slope. Slope is rise over run. In other words, it's change in elevation divided by distance, horizontal distance, between those 2 points where elevation was measured. Let's find the hydraulic gradient in the lower or confined aquifer. At D, water rises to 580 feet, indicating higher pressure. At B, water rises to only 565 feet, indicating slightly lower pressure. Change in elevation, 580 minus 565 is 15 feet, divided by the distance, 4,800 feet, between those two locations. That gives us a hydraulic gradient of 0.03125. No units, because both of our measurements are in feet. Feet divided by feet cancel. Our hydraulic gradient is unitless, which is the form that we would want it in to use Darcy's law. Darcy's law needs hydraulic gradient to be unitless. In other words, it needs the units in which elevation was measured to be canceled by the units in which distance was measured. In other words, you need to measure elevation and distance in the same units, feet, meters, inches, whatever. as long as they are the same. You may also sometimes want to express hydraulic gradient not as a decimal place, like we have here, or ratio, but instead in units of feet per mile, so we get a nicer number. We would convert our unitless hydraulic gradient to units of feet per mile by multiplying it times 5,280 feet in 1 mile. The result is 16.5, which has units of feet per mile. But again, to use Darcy's law, we want hydraulic gradient to be unitless. Darcy's law requires us to know the hydraulic gradient, I, connectivity, which is K. Connectivity is a property of the aquifer material. It's similar to permeability. In other words, it's a rate, say feet per day, some units of distance divided by time. And finally, A is area, which is the width times the thickness of the aquifer material. Let's use Darcy's law to calculate discharge Q, the volume of water that could be yielded by the lower confined aquifer. We already found our hydraulic gradient. We did that on the previous slide. Conductivity of the limestone is a given. How thick and how wide is the aquifer? We need to measure the aquifer material, 40 feet thick by 15,000 feet wide in this case, given an area of 600,000 square feet in this particular example. So we have everything we need to calculate discharge, Q, because I, we found before, K is a given value based on the aquifer material, in this case limestone. K would be different for sand or other types of aquifer materials. Then A is the measured thickness and width of the aquifer. So let's calculate discharge. Gradient 0.03125 times connectivity, 2,000 feet per day, times area of the aquifer, 600,000 square feet. Notice our units. Gradient has no units. Connectivity, units of feet per day. Cross-sectional area of the aquifer in units of square feet. So our discharge is going to be in units of cubic feet per day, of volume per time, which is the right units for discharge. By keeping track of our units, we will know if our result has units appropriate for the variable that we are trying to calculate. We're trying to calculate discharge, which needs to have units of volume over time. We've set up our equation, gradient, connectivity, area. We end up with units of cubic feet per day, volume per time, appropriate units for discharge. What is the result? 0.003125 times 2,000 feet per day times 600,000 square feet. The discharge out of this aquifer is 3,750,000 cubic feet per day. Let's use Darcy's law in a slightly different way to calculate velocity of groundwater flow. Velocity of groundwater flow depends on two things: connectivity, K, the rate at which water is transmitted by the material, and the gradient, or I. Steeper the gradient, faster the velocity. We can get velocity by dividing both sides of Darcy's equation by A. The result, because discharge has units of volume over time, say cubic feet per day, dividing it by units of area, say square feet cancels 2 of those 3 feet, we're left with units of feet per day, which isn't a unit for velocity. So velocity is given by the hydraulic gradient times the connectivity. Let's find the velocity of groundwater flow in the limestone. We take our connectivity, 2,000 feet per day, times our gradient, 0.003125 unitless. Velocity, 6.25 feet per day. Again, that was given by 2,000 feet per day, connectivity, times gradient, 0.03125, unitless, equals 6.25 feet per day. Again, we now have units of length rather than volume over time, which is an appropriate unit for velocity.